This lecture is about mathematical proofs. There are various statements that we need to prove in mathematics. Most of the statements are implications, but we also sometimes prove the existence of a particular object or the uniqueness of a particular object. We begin by looking at existence theorems. An existence theorem is a theorem that asserts the existence of something. For example, the statement, there exists a black sheep named Pedro, and there exists a real number x such that 2x plus 3 is equal to 7 are existence theorems. The way to prove an existence theorem is to put forward a candidate and show that this candidate does precisely what we want. In our first example, we present a black sheep and confirm that this sheep indeed has the name Pedro. In the second case, we consider the candidate x is equal to 2. Since 2 times 2 plus 3 equal to 7, the proof is complete. To prove an existence theorem, you must produce the candidate, which in many cases may require a lot of thinking. However, exactly how you came up with your candidate need not be part of the proof. A uniqueness theorem is a theorem asserting that a mathematical object is unique. Here is an example of a uniqueness theorem. Suppose that f is strictly increasing and that there exists a number x such that f of x is equal to y for a given y. Show that x is unique. The common approach to prove uniqueness is to assume that there exist two real numbers, x1 and x2, which both satisfy the theorem, and show that x1 must be equal to x2. In our example, f of x1 is equal to y and f of x2 is equal to y, which means that f of x1 is equal to f of x2. Since f is strictly increasing, it must be the case that x1 is equal to x2. If x1 is different from x2, say x1 is greater than x2, then f of x1 must be greater than f of x2 since f is strictly increasing. A proof by counterexample is often useful if you want to prove that an implication is false. Given an implication A implies B, we say that we do a proof by counterexample if we produce a value of the variable x such that A is true and B is false. Remember, producing one such example will prove that the implication is false. Here is an example of an implication. If x is greater than 10, then x is less than 20. This statement is false, and all I have to do to prove that the statement is false is to produce a counterexample. My counterexample is x is equal to 30. The hypothesis is true, x is greater than 10. However, the conclusion is false, and this is enough to prove that the implication is false. Here is another example. If x squared is equal to y squared, then x is equal to y. This statement is false. My counterexample is x is equal to 2 and y is equal to minus 2. The hypothesis is true, 4 is equal to 4, while the conclusion is false. Consider the statement, if x is greater than 1, then x squared is greater than x. One way of checking if this is a true or false statement is simply to try a number of possible values of x. There is no point in trying values which are 1 or less, since the hypothesis is false in this case. If we try x is equal to 2, the conclusion reads 4 is greater than 2, which is true. For x equal to 3, the conclusion is still true as 9 is greater than 3. We can try a value slightly larger than 1, for example x equal to 1.1, but the conclusion is still true since 1.1 squared is 1.21. It certainly seems like this statement is true, But unless we check every possible value that satisfies the hypothesis, we do not have the proof. Therefore, we need a strategy for proving this implication, which does not require us to check every possible value. The strategy is based upon using a set of axioms, that is, results that we take as given with no proof. We typically also use definitions and other results that have been proved from the axioms. If the hypothesis is true, then x is greater than 1. One result in mathematics tells us that if I multiply both sides of an inequality by the same positive number, then I will create an equivalent inequality. That is, a predicate that has the same truth value given the free variable as the one we started with. Since x is a positive number, I can multiply both sides by x, and that will give me x squared is greater than x. Note that these two inequalities are not equivalent. They are only equivalent if x is strictly positive. However, the left-hand inequality will imply the right-hand inequality, as x is strictly positive under the hypothesis. This argument works for any real number greater than 1. Note that we use the following strategy to prove the implication. We assume that the hypothesis is true, and then we show that the conclusion must then be true as well. This type of proof is called a direct proof of an implication. Next, let's look at another useful strategy for proving implications, which we call proof by contrapositive. Let's start with an arbitrary implication. A implies B. Here is the truth table for A implies B. Now consider the statement not B implies not A. Not B has the values false, true, the opposite of B. Not A has the values false, false, true, true. Now consider the statement not B implies not A. This statement is true unless the hypothesis not B is true and the conclusion not A is false. This means that the statement is false in this case and true in all other cases. If you compare this to the implication A implies B, you see that these two statements are equivalent. If I want to prove that A implies B, I can just as well prove that not B implies not A. And in some cases, this is much simpler. When we prove that A implies B, by proving that not B implies not A, we say that we do a proof by contrapositive. Here is a simple example. The statement x not equal to 0 implies 4x is not equal to 0. To prove this, we formulate the contrapositive. 4x is equal to 0 implies x is equal to 0. This is trivial to prove. We simply divide both sides of the hypothesis by 4, giving us x is equal to 0, which is an equivalent predicate. The final strategy for proving an implication is called proof by contradiction. To create a proof by contradiction for the implication A implies B, we assume that the hypothesis A is true and that the conclusion B is false. If we, from this assumption, can create a contradiction, then our implication must be true. An example will illustrate the procedure. Let's say that I want to prove that the sum of two positive numbers is positive. The implication I want to prove is the following. If A is greater than 0 and B is greater than 0, then A plus B is greater than 0. We need to assume that the hypothesis is true. That is, we assume that A is greater than 0 and we assume that B is greater than 0. We assume that the conclusion is false. That is, we assume that A plus B is less than or equal to 0. From this, we try to create contradiction. a statement that simply cannot be true given the hypothesis. In our example, let's add minus b to both sides and we have a less than or equal to minus b. By assumption, b is greater than 0, which means that minus b must be less than 0. Since a is less than or equal to minus b and b is negative, it must follow that a is negative as well. We have reached a contradiction since by assumption a is strictly positive, and we have proved our implication. It is possible to design truth tables to show that a proof by contradiction is a valid proof of an implication, similarly to how we demonstrated the method proof by contrapositive. However, we will not do that in this lecture.